I heard people say that this couldn't be done. It'd be an almost impossible challenge to do what we had to do. But our job is to make that possible. When you're finished the project and the hospital opens and you stand back and you look up at it, particularly when you look up at this hospital now, you know, and you say, I was part of that, it's really something actually, you know, and it feels like you're leaving a bit of a legacy behind. So I'm happy to keep doing this for potentially for the rest of my career.
It's a long journey, but in the end, it's, you know, you just have to think about what the finished product is going to be and how wonderful it'll be.
This is a standout project in the career of any engineer.
You get a sense sometimes of how important what you're doing is.
Ultimately, our client is the children of Ireland and everybody in Ireland, their parents as well. I have young kids myself, and the facilities that are there for them at the moment are not really what we would like them to be in this country. So, you know, that's really why we're doing it.
Someone asks you, what do you do? Oh, I work in the children's. Oh, the new children's hospital. Yeah, no, everybody knows what it is, and though they may not say it, everybody knows how important it is. I think they talked about building a new children's hospital in Ireland for 40 years or so.
And I've always loved healthcare work just because of that. It's, you know, it's complex, it's technically challenging, but also it has that social usefulness aspect to it. You very much feel when you're building a hospital that you're doing something that's better for the good, greater good.
But you get a sense sometimes of how important what you're doing is and what it will be, and now you see the building coming up higher and higher out of the ground. You get a sense of how grand it will be when it's finished.
So what Jones Engineering bring to this project is, number one, we bring experience, but more than that, we think we bring a culture, we bring passion, and it's a passion to solve problems. It's a passion to get things done right the first time, to come up with a better way to do things. We're always looking to see, can we innovate and can we come up with a smarter way to do something. But it's also a passion to hand over a project that at the end of the day is a world-class facility to the highest standard.
I think my advice to young engineers who are about to graduate is don't limit yourself in what kind of job or sector you've studied your engineering in. They're all quite versatile and flexible. You can switch from one side to another. It is going to take a bit of learning and getting used to, but you're well able to do it. Definitely just don't limit yourself to something, to just your degree and only your degree.
Ultimately, a consulting engineer solves problems. So clients will come to us with problems or challenges. They may want to build a building in a certain place, or a bridge, or design a table, or anything. And it's our job to decide how that might happen. Can it happen in a cost-effective manner? What are the stages that would have to go through to decide, from concept to detailed design to figuring out a price to production, all of those things. So yeah, ultimately our job is to solve problems.
Yeah, like I think that many times when we finish college or university and we are all very excited about moving into the real world, and sometimes we do believe that we know everything, but it's not really true. And actually, like, you learn the concepts and you kind of learn how to think, and then you come to the real world, and yeah, you are constantly learning stuff. And if you have good managers who help you, that we have them here, and you will start having small tasks, and then eventually they will start giving you bigger tasks, and just do it on not really on your own, but like give you that freedom of, okay, you have to do this, any question, let me know, but you have the freedom to do it on your way. You have to learn how to allocate time to different things, because yeah, there are different jobs within this project, like as a project engineer or as a coordinator, or you have to be interacting with many subcontractors, different trades. You see that it's a huge hospital, and there are many people involved.
I remember when I was in college, or leaving college, I didn't really understand the different roles that were out there in the industry. So there was, you could be a consulting engineer, you could be a contractor, you could be a manufacturing engineer, you could be a technical sales engineer. I had no idea what they were. Okay, I didn't know. I took a job, my first job was a technical sales engineer, and I just saw it an engineer, you know. And And that turned out to be a really interesting job, which I did for a couple of years. But ultimately, the difference between the roles is consulting engineers predominantly design. It's more office-based. We spend time on site. As you can see now, I'm on site and have been here for quite a while. But predominantly, we're office-based, and we produce designs in the form normally of drawings. And then our colleagues, the contractors, actually take our designs and make them into a reality by turning them through fabrication drawings and constructing them and managing the works actually on site. So that's the fundamental difference between consultants and contractors.
And it's a departure, I think it's a departure in the design of hospitals in terms of it's all single rooms, so there's no wards. So there's lots of privacy for the children and for their families, and then in each room there's a bed where a parent or a friend can stay the night in the room comfortably, and that's really important as well for children. And the whole design is very much focused on their well-being, with lots of light and lots of outdoor space, and so all of that hopefully would help the healing process and help them feel more at home and more relaxed in a hospital environment.
So just a little bit about the project itself. I think I mentioned already, I've been personally working on the project for 6.5 years, and I'm really proud to work on the project. I know Arup as a company, we're really proud to work on the project. We pride ourselves as a company that does socially useful work, and no better work to be doing than delivering a hospital, you know. And it might sound a bit corny, but I mean that it's really interesting and, you know, fulfilling work to do. I could be delivering different types of projects if I wanted, but I've worked on hospital projects for most of my career, and I think I'll continue to work on them for the rest of my career. They really are interesting projects. They're very technically challenging. They're very complex projects to work on, and when you're finished the project and the hospital opens and you stand back and you look up at it, particularly when you look up at this hospital now, you know, and you say, I was part of that, it's really something actually, you know, and it feels like you're leaving a bit of a legacy behind. So I'm happy to keep doing this for potentially for the rest of my career. The hospital itself, this project is, I'm not sure people understand the complexity of it and the enormity of it. The building itself is 160,000 metres squared. It's, you know, it's got 6,000 rooms. If you try and imagine 6,000 rooms, that means there's over 25,000 internal walls. Those kind of numbers, they make the mind boggle. They don't mean an awful lot to people. Your average house, for example, is, you know, 150 square metres. So, you know, it's over 1,000 of those. There's over 15,000 square metres of plant rooms alone. So if you take any of the large commercial office projects in the city centre, the overall building area of those will be maybe 15,000 square metres, probably less. And it's like taking one of those and completely filling it full of mechanical and electrical plant. And that's just the plant rooms. We also have to design all of the arteries that connect the plant rooms to the end user. So there's any number of outlets in any of those 25,000 walls with, you know, with electrical services, with medical gas, with very clean water to help wash people's blood. Everything you can imagine is in this hospital. So it's our job as designers to design all of those services for the hospital, from the plant rooms right up through the distribution, to get them to rooms so that ultimately patients, who are our ultimate clients, in the rooms are getting the treatment that they need. The building has, it's, you know, over 5,000 rooms. There's 22 operating theatres. There's over 80 isolation rooms. There's 130 air handling systems. There is over 30,000 data outlets in the walls. The building is phenomenally complex and really interesting to work on. If you're an M&E designer, I don't think there's much that a hospital hasn't got. It's got offices, it's got operating theatres, it's got ICT rooms like data centres, it's got kitchens, it's got restaurants, it may have a cinema. It has everything really that you could want to design, and plenty to keep you interested. So Arup were appointed to start work on the Children's Hospital in 2014, and I started working for Arup on the project towards the tail end of 2014. So it's a really important commission for us, and it's a project that we're really proud to be involved in and committed to delivering. It has been tough at times. but we're really seeing the fruits of our labour now out on site. The building is now up to level 7, so the structural frame topped out last month, which means that the superstructure is largely complete at this stage. And that's something to say as well. Over the years, we've had plenty of social events. The team working on this project, the guys in this building, as well as our own office and in BAM's and Mercury's offices, we've all been working together for a long time now. And we're okay, we have our disagreements, but we work together we work together well the majority of the time, and we really enjoy it. So the M&E fit out now is reasonably well progressed. It's probably 20% through at the moment, and there's quite a way to go, but there's a lot of activity out on site now, so it's quite an exciting time to be based on site. And as you can see with the Lewis going by now, that's one of the things we have to deal with. Yeah, so the location here was certainly challenging in terms of the footprint that was available for the building, and it was well, I suppose, publicised that there was doubts about the site and whether it was the right site for this building. And it's not our role or my role to question the site itself or the location of it. It's our role to come up with solutions to make the building work on the site, and in fact to make the site work for the building as well. The site, obviously, it's a live hospital campus. So there's hundreds and thousands of patients coming into this site on a daily basis, and the St James's Hospital could not be affected by anything that we had to do. We couldn't shut down the hospital or any part of it. They had to provide service to patients 24/7, as they do always. And the really unique part of the piece of work that we're going to talk about today is there was a utility tunnel that connected the St James's campus to its energy centre, which is, if you think about it, it's almost like an umbilical cord, and it transfers all of the critical services from where they're generated to where they're needed. So that's power, keep the lights on, keep all of the machines on, it's heat, it's steam, it's medical gases, it's oxygen, that people are acutely aware of how important oxygen is these days, and nitrous oxide, and various other critical services. And the problem that we're talking about today, that we had to work together with Jones Engineering to solve, is that this tunnel ran through the site for the new Children's Hospital. It ran underground and directly through the route where we needed to excavate to get this building started. So before we could even start, we had to crack this particular challenge. Initially, it's about coming up with a concept, right? So that's really our role at the start. I heard people say that this couldn't be done. I'm pretty sure I read it in the newspapers actually, that this couldn't be done, that there were so many critical services, the Drimna sewer and the utility tunnel running through this site, that it just wasn't suitable for this hospital, and it would really be an almost impossible challenge to do what we had to do. But our job is to make that possible, right? The first thing that we do is we go and visit site. So it's hard to imagine, but there was a first time that I visited this site, and it was about 6.5 years ago at this stage. It was cold. I remember there was 22 old buildings on the site where the hospital is been constructed now, and there was obviously this utility tunnel running underground through the hospital. So the first thing we do is we go out, we survey the site, we familiarise ourselves with where everything is, where everything connects into. We obviously we bring in some specialist companies to help us survey underground to try and figure out where everything is going, where it starts, where it ends, and that allows us to build up a picture of what the specifics of the problem is. And I often think it's like, if you imagine starting, it's almost like a photograph that has very poor resolution. So we start with a concept which is the bones of a solution. It's not very detailed, the resolution is not very good, and as we move through the stages of the project, the resolution gets better, gets better, gets better. So we learn more, we provide more detail, and by the time we get it to the stage where it's ready to be constructed, we've got pretty much all of the detail. We've got everything that the contractors need to build. So yeah, there would have been an initial information gathering stage, let's call it that. And ultimately, if we imagine a situation where we have an underground tunnel running through a site that we need to clear, I think any of us here could come up with the initial concept. The tunnel has to go around the site that you've got to, So we looked at a couple of potential routes as to where it would go, and we decided pretty early that the tunnel needed to run east to the northeast corner of the site, and then south to join back up outside the footprint of the new Children's Hospital. And so that was the initial concept 101. What we had to do then is try and understand, so okay, now I've got an idea. is it feasible? Okay, so we need to produce, what people refer to as a feasible generic design. So it needs to work, it needs to be possible, and it's based on generic components. So we can't specify it must be that exact type of machine. We've got to be able to do it in generic terms so that the contractors can procure from different sources. Okay, that's something we have to work within. So now we've got an idea and we start to develop, okay, well, are the levels correct? Can we get the tunnel physically far enough underground, and will it bump into anything as it's coming along that route? And if it does, how do we divert that? So we go through a whole stage of working with other consultants then. So we work with the architects, we work with the civil engineers, we work with landscape engineers to try and figure out if our initial concept is actually feasible. So where could we start the tunnel? It obviously needs to come out of the energy centre, because that's where everything is generated. So is there a part of the energy centre that's in the right place where we need to come out? Is the energy centre deep enough to come out? The way the levels work over there, the levels is the kind of the slopes and the depths of the ground and so forth. The new building was obviously going to have quite a big basement, and we needed to come out very low, much lower than the existing tunnel was. And so we had to survey the St James's Energy Centre to see, is there a part of that building that's low enough that we could feasibly break through the wall from underground and create a new tunnel and connect everything back. And so we determined there was, we picked a location, and we came up with an initial set of concept design drawings, which we used predominantly to agree the scheme design with the key stakeholder at this stage was St James's Hospital campus, because they own the services, they're keeping their hospital live, we're doing open heart surgery on it effectively. And they needed to agree, we needed to get their agreement with everything that we had to do. We produced an initial set of concept drawings for all of the main services, so for the electrical services, steam, medical gases and so forth. And we set them up in a way where we showed schematically existing. Next page would be proposed intermediate stage, and the next page would be the final stage. And we set them up, it's very basic, but just in a way where you could flick from one sheet to the next on a projector, and it was very clear to this client what was changing at each stage. So, we would add a new bit, we would make a connection here, we would run services here, we would make a changeover at this point. And we had to demonstrate to St James's that we could do it in a way that would be safe and that it would not cause an interruption to their operation of the hospital. That was just a no-go. We could not do that, we couldn't interrupt the services. And we had to give them confidence that we had designed it in such a way that this could be carried out in as we had designed it. So we sat in long rooms like this with our drawings up on the screen. All of the people from the St James's Technical Services departments, their Director of Capital Projects, all of the key people over there, including clinical people as well. So you would have some of their clinical engineering leads and people who understood what it meant if their oxygen supply turned off, for example. Yeah, so to give the St James's team confidence that the solution that we had come up with was buildable and could be implemented in the timeframes that would avoid any downtime on their systems. We collaborated with contractors prior to having the meetings, and we were able to demonstrate that we had thought through the turnaround times for controlled shutdowns and for switchovers between one service and another service and backup services and that type of thing. We developed our concept, we satisfied ourselves internally first, which is the most important. We would have done internal peer reviews within Arup, of course, to make sure that the design that we had come up with was solid, it would work, it could deliver what it was we needed. We then obviously got that agreed with the stakeholders in St James's Hospital and indeed with our own client in NPHTB and CHI. So now we have something we can work with. And we moved then to the tender design phase, okay? So really where we're trying to head here is to try and engage. We want to be able to now contract this piece of work to a team of contractors who can actually implement it. So the next stage of the project that we need to move to is developing a tender design, okay? And what tender means basically is a design that can be priced, it can be costed. Contractors can provide a price to go and deliver this piece of work, because now that we have a concept agreed and we know where we're going, we need a contractor now to build this for us. And with public projects, the way they're procured, you've got to advertise it online. You let contractors tender for it in a fair way. And we need to produce a very detailed set of design drawings now, or tender drawings as we refer to them, so that all of the contractors get all of the same information and that they get a period of time to assess those drawings, measure them and come back with a price. So all of the contractors submit their prices for the work, and the contractor with the most economically advantageous tender wins the project. So not necessarily the cheapest, they have to demonstrate that they've thought through the methodology of how they're going to approach the works, and they get points for that, as well as getting points for having an economically attractive tender as well. So we need to take our concept drawings at this point and develop them into something more detailed. So we need to add all of the valves, we need to add all of the right pipe sizes, we need to add all of the material specifications, we need to add all of the accessories that aren't necessary at concept stage. So when we're agreeing a concept with the stakeholders across the road, they don't really mind, if there's 2 sets of expansion bellows or 1. They just know you've got to have them, you've got to have thought that through. But for tender, you've got to have designed all of the valves, all of the accessories, so that they can be counted and all of the contractors can price them in a fair and an equivalent way. So it's taking the concept and it's developing it into a detailed set of drawings that plugs all the gaps. And as well as your drawings, you produce specifications, which are documents which list out all of the material specifications, all of the constraints, all of the duties that the contractor must carry out, all of the everything which will cost money effectively, and everything which is required to complete the work. So we prepare a big pack of drawings and documents, mechanical and electrical, which go together and they're sent to the contractors to price.
It was going to be the biggest project in Ireland, so it was always a project that was of interest to me. I always personally wanted to be involved in the biggest and the best projects, but even as a company we always want to be involved in the biggest and the best projects. A tender process was held in summer 2016, and it was a huge undertaking to actually price the project, never mind construct it. There were over 1,200 mechanical drawings alone. We spent 4 to 5 months pricing the project, and thankfully then in summer 2017 we got awarded the mechanical services installation for the project. And right from the outset we had some of the team members involved in pricing the project. So currently we've a team of about 350 people working on the project, and it's this team of managers and engineers and craftspeople that actually make this amazing project possible.
I had worked with Jones Engineering on the St. Vincent's Private Hospital project a number of years ago, and that was a very successful project. So we were delighted when Jones won the contract on the Children's Hospital, and we knew that the quality of the work in particular, would be to the highest standards. And I think that Jones hold those values. They want to walk away and leave the thing running well and not have any comeback at the end of the day. And again, realize the importance of a hospital project and making sure that everything is working and that there isn't downtime. So I think the working with the contractors brings that buildability element. Sometimes as designers, the kind of physicality of how you actually fit something in, how you put something together and how it fits in the space is not something that we'd be as strong on. And so it's great when the contractor comes to the table and the whole thing starts to become real. And Jones certainly brought their skill in prefabrication and modern methods of construction to the table, and looked at what we designed and saw how it might be tweaked to make it more what you might call more easily constructible or more easily prefabricatable.
So the terminology we use is coordinated. So and the terminology in the industry is the consultant produces feasible generic design. Yeah. Which, as I said, is a design that can be built, is based on generic equipment, and then the contractor takes that and turns it into a specific set of construction drawings. So it's fabrication drawings based on specific products. So he will actually know exactly what valve, exactly what brand of pipework, exactly what type of pumps and fans and so forth, and they load all of that into the design now. So you go back to the resolution thing. The resolution is getting really down to the last couple of millimeters now, and they know exactly how everything is going together. So we work with the contractors at that point because they have They have an element of design development in what they do. So, you know, you could call it coordination, you could call it design development. Ultimately, it's taking our design and turning it into something that can be fabricated.
So we initially received the design from Arup, and obviously straight away there's a brief overlook at the entirety of it. And then we really get down into the nitty gritty of it. The design in some ways are quite conceptual, and we have to make that a reality. And that starts out with large concepts of how are we going about taking it and physically doing it, and what does the end goal look like in that regard. And if you take the likes of the utility tunnel that we worked on here, the major concept really was modularization, and that's mainly based around speed. So are you going to just get all the materials delivered here to site, or are you going to actually get them delivered elsewhere, actually put hours off site elsewhere and bring finished elements to site? And it sounds slightly trivial, but that's a major decision you're going to make. You're going to need off-site premises, you're going to need insurances, you're going to need logistics, additional transport over and above. The level of coordination that's required is going to have to be probably an order of magnitude higher, because everything has to come correct. There's no bring it here and sure we'll fix it, but that just defeats the purpose of what you were trying to do in the first place. So, and more and more as the industry tends to go in that direction, the more and more accurate you have to be. People coming straight out of college, there's not really any much time to come up to speed. You got to kind of be there from the get-go and get in with a more senior engineer and do your best to play catch up and roll with them. Yeah, so one of the things that we try to employ when we are doing a review of the design is a simplification of it. A pipe that runs in a straight line is far simpler and easier to install than one that has multiple changes of direction in it. From a cost point of view, but also from a system operational point of view, there are benefits to everyone from a simplification. And that really leads into how we think about offsite fabrication, where we're endeavouring to provide compact, repetitive items delivered to site, high quality, low issues, and the simpler that we can make these things, the easier it is to repeat them, the less number of issues you can have with them, and that just leads to higher quality and reduced time overall, really. Yeah. To facilitate the speediness of the shutdown works, we needed to prefabricate as much pipework as we can. Now, in an already installed environment, it's very difficult to provide accurate prefabrications because you're relying on what you can see and measure and the accuracy of that. So the entire junction where the cut-in was going to take place was 3D scanned with LiDAR, and this provided us with an accurate base point that we could insert into our model on top of that, and we probably saved in the order of 4 to 6 hours of work on site, and that's 4 to 6 hours of real time of a hospital losing their heating system that was saved. So in the case of this project, off-site manufacturing was deemed an absolute necessity over a nice to have, due to a number of factors, the restrictions in and around this relatively tight site, but also, and more importantly, from a quality point of view, where it's far easier to control quality in a controlled off-site fabrication facility, and the number of other factors that go along with that: reduced health and safety concerns on site, reduced issues due to inclement weather. One of the most critical and things that was identified earlier on was how the diversion of the steam systems would be handled. The steam is used to provide heating to a large part of the existing hospital, as well as hot water services, and as you can imagine, turning these systems off, it's life safety critical for patients. So it had to be handled in a very controlled manner. This was done through writing a very large document about method statement about how the process would be done and how it would impact on the hospital especially. There was a location identified where the two tunnels will connect, and at this location we had to cut in several T's and valves to be able to facilitate the diversion at a future point. And this was done over the course of 6 Saturdays and through normally in Saturday nights to provide the least disruption as possible. The hospital identified this as the best time of the week to do it, based on very low number of surgeries and stuff likely to happen on a Sunday morning. So we would shut the steam system down, allow everything to cool down and the pressure to drop. We would then cut into the pipe at the identified location and add in what was required with the additional valves. This typically took in the order of 6 to 8 hours, and we would work through Saturday night into Sunday morning, maybe finish about 2 a.m. So by 8 a.m., 10 a.m. Sunday morning, the heating systems were available again to the hospital. And in addition to the steam systems that serve the hospital, the utility tunnel is also home to a number of medical gas services. That includes medical or surgical air and nitrous oxide, laughing gas. So these two systems are critical systems to the health of the patients within the hospital. And one of the critical milestones that we had to carry out was a diversion of these two gases. Now there was no additional valves for us just simply to tie on, so you couldn't just plug in and close a couple of valves and change it over. We had to completely shut the system down. Now these services provide air to ventilators and to other critical components, surgical devices within the hospital, as well as the nitrous oxide that's used for anesthesia. So the system had to be shut down, and inside the hospital then was brought in the order of 100 cylinders of gas, and these were all plugged into the hospital locally to provide services to the patient while the works were taking place. Again, in the middle of the night, I think it was finished in the order of 4 a.m. to provide the least amount of disruption to the hospital. The project here is utilising BIM as a resource. More and more the industry is moving towards 3D software as a way to provide accurate installations and reduce issues that arise on site from clashes. And this was the case here. The project utilises Revit, but also for the utility tunnel we used another software called Plant 3D to be able to better facilitate prefab off-site. The design concept model that we get from Arup really acts as a schematic, so we know that what needs to go where is the most important thing to fulfill the design. The entire surfaces within the tunnel then are each meticulously modelled in 3D, not just the pipes but all of the supports that go along with the pipes. And this then is, once it's completed and we're happy that it all works and it flows well and it's as optimized as it can be, is then broken down into modular sections that can, individuals or drawings are produced for these sections, and then that's taken away and fabricated off site. But the model acts, in addition to just providing the information that's required to build it, it really gives a level of reassurance and a check on the design that everything works. At the end of the day, a tunnel is a closed box. You can only fit so many things in it, plus you have to fit people in there as well. So it validates at a very early stage that there's not really going to be any fundamental problems on site, and it gives everybody confidence then to move forward to the construction phase. One of the key considerations that we have, and especially as time goes on, is the reduction of waste and optimization, not just for the environmental sake but also from a cost point of view. It's beneficial. So when we look to modularize, we look to try and use as many standard components as we can. For example, pipe that comes straight from the mills in Asia typically comes in 6 or 12 meter lengths. You can make a module any length you want, but you can end up with a load of offcuts that have to go in the bin. So the actual modules were manufactured around the standard lengths of pipes. It leads to less waste, less work on site really, and beneficial overall. These models contain so much information, but information is no good if you can't communicate that information. And the currency of communication is still 2D drawings. In the case of this system, but really in all systems, one of the key considerations for pipe install is how to deal with thermal expansion. And in the case of steam, because you're operating at higher temperatures and pressures, this is especially so in this case. The system as a whole is sent out to a expansion specialist, and they provide the critical locations and information about where we should allow for expansion, how we should restrict the pipe movement. Really, it comes down to where do you not want the pipe to move, and where do you want a pipe to move, and what are the loads going to be as such of this. So typically you end up, a simple example would be where you have an expansion bellows and you have an anchor in between, and you allow the pipe to expand into that bellows in a controlled way. If you were to not provide any expansion control and simply turn on a system, materials expand, materials move, but they will do it in an uncontrolled manner in a way that you can't predict, and it could damage the system, it could damage an adjacent system. So it's critical like this that this check is done, and also not only done but incorporated from a very early stage, which was the case here, where we can incorporate the expansion design into our modularization. And again, it's just another element that comes to site already complete, really. Yeah. So the thermal expansion design that we've mentioned before, here we can see it now in action on site. Typically between each of the 13 modules you'll see a set of axial expansion bellows, and these allow the pipe as it heats up to move and expand in a controlled manner to a set location. The bellows are then guided by pipe guides to restrict any lateral movement that could cause the bellows themselves to buckle. And then to the left of the bellows, you see the pipe physically anchored, welded in this case to the frame to restrict the movement at that location. And that setup is typically repeated throughout the entire tunnel. The real work starts when you have to start installing surfaces on site, and it's the quantity and the quality of the decision making that you make really will dictate how the project goes. You have subcontractors or labourers, relying on you to provide them direction, and making key decisions to change something along the way, though may be painful, will ultimately benefit the project in the long term. Yeah. So one of the benefits of the prefabrication on this element of the project, and given the amount of welding that was required, is a significant reduction in on-site weld. Welding can be quite a slow, laborious process, and particularly if you don't have great access to where the weld is required to take place. Being able to do these welds in a workshop means generally higher quality, quicker, and less risks associated with fire. Welding is carried out at great temperatures, and fire hazards on site obviously are particularly of importance. In some ways, once the installation is complete, the most difficult work of the project actually starts, and that's in the testing and the commissioning phase. And with any pressurized system, all the systems have to be pressure tested to a set pressure, and over a number of hours, and this determines if there's any leaks within the system. Unlikely there would be, given the high level of quality, but if there was, this would detect them and they could be remedied. Once the system is practically complete, you're ready to move forward to the commissioning phase. In this case, because the existing plant was already live to an operational hospital, this had to be done in a very controlled manner. It was critical that we didn't interrupt any of the service to the live hospital while we underwent these tests. Unlike the shutdowns that we did late Saturday nights, these were going on midweek while there was surgeries and everything else happening within the hospital. So we were satisfied that the system operated correctly. There was no leaks caused by the thermal expansion within the system, and we were happy enough to proceed towards the changeover. And like before, It was done over Saturday night, Sunday morning. The existing plant was shut down. All of the changes were made to allow the system to flow through the new utility tunnel, and it was brought up slowly, and that's very important with steam. Steam, if brought on too quickly, could cause thermal shock to the system or uncontrolled thermal expansion, or steam hammer, which could result in an actual rupture of the pipe. So you're bringing the temperature and pressure up slowly over maybe an 8 to a 10 hour period. And at that stage you are live to the new hospital, and all of the services that flow through the old tunnel are now redundant. In addition to that, the MEG gas, the electrical services are all brought online, and now the links to the old tunnel can be severed, and the old tunnel can be demolished and taken away. And meantime, the hospital has operated regardless, and no disruption to service was seen by any patients. Really, the challenges associated with this project revolve around primarily its location. You're adjacent to an existing live hospital. You're in a very busy part of the Dublin suburbs. You've got houses on all four sides of you, very, very close residents. You've got the Lewis going past every 15 minutes. And that everyone has to bear consideration towards that. These people will still all be here when the building is finished and we're long gone. So there had to be a rapport built up with the neighbours, and I think it's managed well. We try to do the best that we can in terms of noise or pollution or dust. Certainly manufacturing off-site, you're reducing the number of bodies here on site, and it all feeds into a kind of holistic way of building. Yeah.
Just what you learned in college is important, very important. It helps you thinking, but don't be frustrated if you don't get good marks, because in the end you are gonna go to the workplace. You are gonna learn there what you have to do and how to do it, and probably the top in the class of your promotion wouldn't have the abilities or the interaction with people that other person who has lower academic grades have. So just take it as, all right, I have to learn all the maths behind and all the everything behind how things work and so on, and try to understand it. But don't get frustrated if you don't get like super good marks, and if you are a hard worker and you pass your courses and your degree, and then you go to the real world and you put all your intention, you will get it. Like, it's just about intention and being eager to learn more and grow professionally every day. Like, that's what I think. So don't be frustrated and move forward.
So I think your degree is not your be-all and end-all. So what you study in college is not exactly what you will work with. Technically, what I'm doing now is a lot of building services engineering, which I wouldn't have studied in college. So like heating systems, I would have done water flow, but I wouldn't have done the heating aspect. I would have done small aspects of it, but not at all. So I think my advice to young engineers who are about to graduate is don't limit yourself in what kind of job or sector you've studied your engineering in. They're all quite versatile and flexible. You can switch from one side to another. It is going to take a bit of learning and getting used to, but you're well able to do it. Definitely just don't limit yourself to something, to just your degree and only your degree.
My advice to somebody that's considering doing engineering would be, I think, just go for it. The options are limitless, I think, at that stage. You have to dream big. You have to really, don't limit yourself by what you think you can achieve, because I think with engineering you can achieve anything you want.
Yeah, I mean, there's not a person that someone asks you, what do you do? Oh, I work in the new children's hospital. Yeah, no, everybody knows what it is, and though they may not say it, everybody knows how important it is, I think. And certainly, we started out 4 or 5 years ago with 3-4 people, and now there's an office here in Jones of 50 people plus the people who aren't even working out of this office. And there's a real, I would say, team spirit, a camaraderie, and a great structure that we have here. You know, it flows well, and I think everybody gets on with everybody else. And certainly from my own point of view, I went from being a relatively new junior engineer to the company now to being a project manager and working with several junior engineers below me. And it's a privilege really to be in that position sometimes, because it's you're guiding people, and it feels like it's important. You know? Yeah. Fundamentally, I think every day on this project you're learning something new, and I think as a result of that, it's certainly raising the bar, not just for this project, but for other projects that the Jones Group are doing at the moment. And also going forward, it will produce a whole new class of engineers that didn't exist within the company before. And whatever the next project is that we go on to, it'll really stand to them.
Yeah, I think what's really exciting to see on the project at the moment is, you know, when you develop a design and you see it on paper and you look at it, obviously I think one thing that's important to mention is that this whole building has been designed in 3D, so using Revit, using BIM, you know, that's pretty much par for the course nowadays, but bear in mind this project started in 2014. BIM was relatively new back then, so the design has been carried out in 3D, it's been delivered through Revit, and the Revit models are then transferred over to the contractors at the stage where they get appointed. And it's been really excellent to work with the contractors to see them take our models and develop them through the fabrication process, through the construction process, to take our designs and turn it into something that's ready to be constructed. And that takes a lot of hard work, it takes a lot of collaboration, it takes a lot of good communication, it takes a lot of patience. There can be disagreements about whether something is going to work or whether something has been set out in the best way for the project, or whether a change is a good thing or not. And there can be conflicting interests at times. Emotions can get high, but we found a really good way to work with Jones Engineering, with BAM, with Mercury, and with other project stakeholders to, you know, there hasn't been a problem yet on the project that we haven't solved. It isn't easy, but we get there.
I've young kids myself, and I understand what it's like to spend time in the current paediatric facilities. They're just not fit for purpose anymore. The doctors, the nurses, the parents, the children of Ireland, most of all, they deserve something better. And I think this project, as you know, we as a team and we as a company, we're doing our part to try and help that and fix that situation. This is a standout project in the career of any engineer. Technically advanced, it'll be one of the most architecturally striking children's hospitals in the world.